So we have these two properties of a sine wave, amplitude and frequency. One thing to notice is that these two are actually unrelated to each other. For example, if I have this ball oscillating with simple harmonic motion at an amplitude of 5 centimeters, the frequency is 1 hertz. If I change the amplitude to 10 centimeters, the frequency is still 1 hertz. To prove that to you, here are two side-by-side slowed down videos of me releasing this ball into simple harmonic motion. On the right, I give it an amplitude of 10 centimeters, and on the left, I give it an amplitude of 5 centimeters. You can see that even though the ball on the right goes a lot farther up and down, it does so with the same frequency as the ball on the left. They both have the same number of cycles per second. So, how do we change the frequency? Well, the frequency is a property of how we set up the object that is oscillating. This spring has a certain stiffness to it, and this ball has a certain weight. And if we change those properties, then we're going to have a different frequency. To show that, we have another spring here, and if we pull it down to 5 centimeters and release it, we can see that it goes up and down much more quickly, and so it has a higher frequency. In this case, the higher frequency comes from a more stiff spring because it is made of a less flexible kind of metal. And so it pulls the ball back to the center much faster than the other spring does. Now, it's always good to look at what happens on our position time graph to see how it looks after changing these parameters. We have here a sine wave on a graph, which represents how our original ball is moving on the spring when we release it at an amplitude of 5 centimeters. We can see that the maximum distance from the center in either direction is 5 centimeters, and the frequency is 1 second. So what happens if we make the amplitude 10 centimeters? Well, these maximums are going to extend at plus 10 and minus 10 centimeters. And so our graph looks like this. You can see that the motion now gets further away from the center point compared to the last graph. But notice that the frequency of the oscillations is still the same. Each cycle still only occurs 1 time per second, giving it a frequency of 1 hertz. So, what happens when we change to the other ball and spring? Well, we can pull it to minus 5 centimeters and the frequency is higher now. On the graph, what we do is we change how often the cycles happen. And in this case, you can see that they happen more often than with the other spring. Even just looking at it, we can see that there are more cycles than what we saw before. More cycles in the same amount of time equals a higher frequency. If we had a lower frequency oscillations, this, we would stretch out this wave and see a lower number of cycles in the same amount of time. And once again, notice that the amplitude of the wave has not changed. It's still 5 centimeters. Whether we have a higher or lower frequency, the maximum distance from the center is always 5 centimeters. When we create an oscillation that follows simple harmonic motion, we always have to remember about these two properties, amplitude and frequency. We can control the amplitude by changing the maximum position of the oscillation. And we can change the frequency by changing the properties of how the object oscillates, like using a stiffer spring or a ball with a different weight. Make sure that you understand these two concepts well, because we will use them a lot in our study of musical sound later on. Speaking of sound, when are we going to get to it? Well, we're almost there. We almost have all of the ingredients we need to start talking about where sound comes from and what all this oscillation stuff has to do with it. We've talked about how we create oscillations in the real world, but we also need to talk about how oscillations behave after we create them. Let's have a look at that.